This training video has been prepared for automotive mechanics who are trained in the repair and servicing of automotive vehicles and the use of related tools and equipment. The information contained in this training video is general in nature and does not contain specific advice or repair instructions. We recommend that automotive vehicle repairs are carried out by a properly trained and qualified technician and in accordance with the manufacturer's instructions. When working on automotive vehicles, always use appropriate safety equipment and procedures. Welcome to Autotech's training video for direct petrol injection. Along with this DVD, you'll have received a technical training manual which we'll refer to throughout the video. On the back of the manual, you'll find more of our training material available from Autotech by calling the number 1300 300 352 or contacting your Repco account manager. Direct petrol injection, or DPI, was first invented in 1925 and was subsequently used in military aircraft engines during the years of World War II. Unsurprisingly, the first automotive application of DPI was initiated by Bosch in the 1950s. Over the following years, many experiments were carried out by Bosch trying to make this technology a success. But DPI was temporarily discontinued due to its high cost with little gain. Stepping forward into the modern era, it was Mitsubishi in 1996 that became the first mass producer of direct petrol injection technology. Since that time, nearly every mainstream manufacturer has designed and implemented their own version of the technology. Before we move forward, there are 4 questions on the screen to have a think about. What do homogeneous and stratified mean? What is an oxides of nitrogen storage catalyst? Why do some DPI vehicles use a vacuum pump? And what would you expect the resistance of a DPI fuel injector to be? If you don't know the answers to these questions, they'll be revealed throughout the video. We'll review these questions and answers at the end to see how you went. The topics that we'll cover during this video are the operating fundamentals of direct petrol injection. We'll look at the different components that are used and the repair and diagnostic procedures of each of them, the requirements for servicing, common issues that have been brought to our attention, and E85 fuel technology. A regular question we get asked is, why are manufacturers replacing traditional EFI systems with DPI? After all, a DPI system is more complex in both mechanical and electrical components. The answer is its ability to lower the exhaust emissions. This chart shows clear evidence how exhaust emission levels have become tighter over the years and will continue to reduce in the future due to the requirements of Australian design rules. One of the biggest drivers of technology improvements in an engine is the car manufacturer's need to reduce exhaust emissions. A byproduct of reducing the emissions is lower fuel consumption. This chart shows how much of an improvement DPI can have on fuel consumption when compared with the same engine on a previous model. Remember, this is exactly the same model vehicle, the only difference being the fuel delivery method. Manufacturers are constantly searching for ways to improve fuel economy and ultimately reduce exhaust emissions. A list of technologies currently possible is shown here, showing each respective fuel saving. The column on the right indicates how beneficial DPI technology can be when compared to other technologies. Peak engine power and torque also increases when DPI technology is compared to traditional EFI systems. As an example, The Hyundai shows a power increase of 16% when compared to the previous model. So how many makes and models can you think of that have direct injection fitted? Here is just a small list of some of the most popular vehicles in the Australian market that use DPI. At the time of this video production, there were well over 1,500 models delivered by 24 manufacturers using direct injection technology. The first vehicle sold in the Australian market was an Alfa Romeo GTS back in 2003. Each manufacturer gives a different name to their engine design. Here are just a few of those names or trademarks that you're likely to see under the bonnet. Some of these trademarks look very similar to those used on diesel engines and could easily confuse you if you're not careful. When describing how direct petrol injection systems work, some unusual terms are used. These words describe the different operating modes of a DPI system. These words are homogeneous charge mode and stratified charge mode. Homogeneous means it's uniform in structure or composition. Putting that into real terms, it means that the fuel and air combination are well mixed in the cylinder. Stratified means to form layers. This is the opposite of homogeneous and describes when the fuel charge remains densely packed below the spark plug electrode. First, let's explain homogeneous in a bit more detail. As the piston starts the intake stroke, air enters the cylinder through the intake valve, and fuel is injected into the incoming air, resulting in a fairly well mixed or homogeneous air-fuel ratio. We also know this as stoichiometric ratio at about 14.7 to 1. A benefit of injecting fuel into the air as it enters the combustion chamber is that the energy required to evaporate the fuel comes from the air itself. That air then cools as a result of the evaporation, effectively increasing the density of the air. The rest of the combustion cycle is similar to that of traditional EFI port injection. Now let's look at stratified mode. As the piston starts the intake stroke, you can see that only air is entering the cylinder. You'll also notice that the intake manifold flap has closed off one manifold port. When the piston reaches the bottom of the stroke, you'll notice there is still only air entering the cylinder. As the piston starts to compress the air, the shaped piston crown starts to have an effect on the way the air moves in the cylinder. It starts to loop upwards toward the spark plug electrode. Nearing top dead centre, the fuel is injected. It's deflected upwards towards the spark plug by the shaped piston crown and focused in the area of the spark plug electrode. You can see here how the contents of the cylinder have become layered or stratified, forming a rich fuel mixture around the spark plug, leaving the remaining lean mixture to form a layer which insulates the cylinder wall from the heat of combustion. Stratified charge mode injects very little fuel compared to that of homogeneous mode and can produce an air-fuel ratio of as little as 60 to 1. There are a few variations of these two main modes. One of these modes is homogeneous lean charge mode. This works the same as the basic homogeneous mode, but runs a leaner air-fuel ratio of up to 22.8 to 1. The throttle plate will open to a greater amount to maximise airflow into the cylinder. There are also various other injection modes that use a combination of both homogeneous and stratified. A combined homogeneous and stratified mode injects a lean fuel mixture on both the intake and compression stroke during changeover between the two different modes. Homogeneous split mode will inject fuel in both the induction stroke and late in the power stroke to enable the catalytic converter to warm up quicker from the hot exhaust gases. This mode only operates for approximately 20 to 40 seconds after startup. Homogeneous knock prevention mode means that under full engine load, the engine can receive 2 separate fuel injection events per combustion. This means that the ignition doesn't need to be retarded when engine knock is sensed, meaning peak power output can be maintained. Stratified charge start mode is used during cold engine starts. This way, the fuel vaporizes quickly and doesn't wash the cylinder walls. This also ensures maximum fuel efficiency and minimal emissions during cold starts. This technology is great, but how many of these modes does Australia use? Unfortunately, the answer to that is not many. The main reason for this is due to the high sulphur content of Australian fuel. Most of the stratified injection modes burn at quite high combustion temperatures. 2 unwanted gases are caused by this combustion heat: oxides of nitrogen, which are fairly easy to control, and oxides of sulphur, which are much more difficult to handle. When a fuel mixture leaner than the stoichiometric ratio of 14.7 to 1 combusts, the nitrogen gas present in the air burns or oxidizes and becomes what we know as oxides of nitrogen, or NOx. The NOx produced by lean engine operation can be reduced to some extent by mixing EGR with the incoming air to lower the combustion temperature. However, the EGR method will only work for lean mixtures up to about 22.8 to 1. To control NOx for the ultra-lean 60 to 1 air-fuel ratio that stratified charge mode is capable of, the vehicle requires a NOx filter in the exhaust system. A NOx filter essentially looks the same as a traditional catalytic converter, but contains a chemical called barium oxide. When the filter temperature is between 250 and 500 degrees centigrade, the NOx gases are trapped in the barium oxide substrate. When the filter becomes soaked in NOx, a NOx sensor triggers the PCM to temporarily burn at a slightly richer homogeneous charge mode to regenerate the NOx filter. This system works really well to control excessive NOx gases, until you add sulphur to the equation. The high levels of sulphur found in Australian fuel oxidizes in the combustion chamber and generates oxides of sulphur, or SOx. Unfortunately, SOx gases are chemically similar to NOx gases and are also trapped in this filter, but can't be removed by the vehicle's regeneration process. This is the reason that the Australian market can't use the full capability of stratified injection mode, as it only operates properly with fuels containing less than 10 parts per million of sulphur. Australian fuel currently has up to 50 parts per million in premium unleaded petrol and up to 150 parts per million in regular unleaded. There are currently 3 engine construction configurations for direct petrol injection: spray-guided, wall-guided, and air-guided. Each configuration requires its own style of piston crown that can be seen here. With the spray-guided type, the injector points down at the top of the piston with the spark plug electrode in close proximity to the injector nozzle. The injector sprays the fuel into the combustion area below the spark plug. The wall-guided injector points at approximately a 90-degree angle to the shape on the crown of the piston known as a wall. The piston wall directs the rich air-fuel mixture into the desired combustion area directly below the spark plug. The third main type is the air-guided injection setup. This engine construction sprays fuel into the general area of the spark plug, then uses the turbulence created by the incoming air to concentrate the fuel charge below the spark plug. These engines have been designed by engineers to produce air swirl and tumble patterns that will assist the intake air charge to correctly mix with the fuel. Be aware that modifications made to any of the components related to the intake or exhaust system may result in fuel usage or emission levels increasing. We'll quickly recap the benefits of using direct petrol injection. We get an increase in volumetric efficiency due to the fact that the fuel injector tip and fuel spray no longer obstruct the incoming air. A cooler combustion temperature can be achieved due to the evaporation of the fuel inside the cylinder, having the effect of cooling the air charge. The cooler combustion temperature allows the use of a higher compression ratio, resulting in the same power output from a smaller engine capacity, better fuel economy, and lower emissions. All of these advantages are further enhanced with the use of a turbocharger or a supercharger. The next section of this video will walk you through each of the components that you're likely to find on a vehicle fitted with direct petrol injection. The engines we're going to use as examples are the 2.3 litre turbo engine fitted to the Mazda 3, 6 and CX-7. The 2 litre FSI engine from the Volkswagen Audi range. And the 3.6 and 3 litre engines fitted to the Holden Commodore and Captiva. Let's start with the fuel system. The first component we'll look at is the in-tank fuel delivery unit. The fuel delivery unit is much the same as that of a port EFI injection system. It delivers fuel at a relatively low pressure, and all three vehicle models that we're going to look at in this video have the ability to vary the pressure during idle and other low-demand situations. This pressure reduction reduces any unnecessary heating or agitation of the fuel, which results in less evaporative emissions from the fuel tank. These fuel senders will normally contain a fuel level sender and in some cases incorporate a filter. Let's have a look at each model specifically. You'll notice that the manufacturer's logo appears when we look at specific models. In this case, on the top left of the screen, you can see we're looking at the Mazda setup. The Mazda system delivers fuel at a pressure of between 410 and 490 kilopascals when tested with a scan tool. I'll explain how to do fuel pressure testing a bit later on in the video. This is a non-return type system, and the ECM can control the pump to operate at two different speeds. The fuel pressure is reduced at idle using a 0.3 ohm resistor in line with the power supply. This pump contains an integral fuel filter with a replacement scheduled every 150,000 kilometres. Access to the pump can be gained by lifting the rear seat. The Volkswagen fuel pump uses an external fuel filter, which incorporates a pressure-limiting valve. Like the Mazda, this pump can be accessed by lifting the rear seat base. Its speed can be varied by the ECM to suit the exact needs of the engine. The fuel pump speed is controlled by the ECM via a fuel pump control module using a pulse width modulated signal. The red shape you can see here is the control module mounted to the fuel pump access plate. The fuel pressure can vary anywhere between 50 and 500 kilopascals, depending on engine demand, although on startup, this pressure will temporarily increase to 650 kilopascals. Interestingly, this fuel pump is energised as soon as the driver's door is open, allowing the fuel system to prime well before the ignition is turned on. This is a close-up of the Volkswagen fuel filter. The scheduled replacement of this filter is every 90,000 kilometres, and you can access it from below the vehicle. This system doesn't return fuel back to the tank during normal operation. The fuel return line that you can see is used only as a fail-safe if the pressure of the fuel increases above 680 kilopascals, 30 kilopascals above the maximum working pressure. The Holden fuel delivery unit is variable speed, and can deliver fuel pressure between 345 and 415 kilopascals. A replaceable filter is located within the unit. The 3.6 litre pump can only be accessed by removing the fuel tank from the car, and there is no scheduled replacement for the filter. The 3 litre pump is easily accessed from below the rear seat. The scheduled replacement for this filter is every 90,000 kilometres, but only under severe operating conditions. The fuel pump speed is controlled by the ECM via a separate fuel pump module. This module can be found below the battery in the luggage compartment. These modules communicate via the high-speed CAN network. The fuel pump control module sends a pulse width modulated signal to the fuel pump to vary pump speed depending on engine demand. A fuel pressure sensor in the fuel line provides fuel pressure feedback to the control module. At maximum pressure, the fuel pump control module will deliver 15 amps to the fuel pump. Saddle-type fuel tanks are used by many manufacturers, including Holden, and are designed to accommodate the tail shaft. A transfer pump is used to transfer fuel from one side of the hump to the other. There are two ways of transferring fuel. An active transfer pump is a second electric pump that operates independently of the main fuel pump. A suction transfer pump is not electric, but uses pressure from the electric pump to pull fuel over the hump using the Venturi effect. The Holden systems use a suction transfer pump. The next component we'll look at is the low fuel pressure sensor. The low pressure fuel sensor in the Volkswagen system is located on the high pressure fuel pump housing. This sensor provides feedback to the ECM, and this sensor's reading can be checked using a compatible scan tool. The sensor on the Holden is located on the driver's side of the fuel tank in the fuel line. You can access this sensor from under the vehicle. This sensor is connected to the fuel pump control module, and the pressure can be checked using a compatible scan tool. Mazda do not use a feedback sensor for the low pressure fuel system. As mentioned earlier, a scan tool can be used to check the fuel pressure. However, there is also a manual procedure for doing this. On the Holden system, you'll find a Schrader valve located between the inlet manifold and the firewall. Here's another view of that valve using a schematic diagram. Holden direct petrol injection systems also use a fuel pulsation dampener in the fuel system. This is designed to minimise any ripples in the fuel pressure caused by the high-pressure fuel pump operation. Mazda's recommended procedure to test the low-pressure fuel supply consists of an inline pressure gauge and a compatible scan tool to activate the fuel pump. If you don't have a scan tool, this can also be done manually. You won't find this procedure in your training manual, so write this down for future reference. Here's a diagram of the relay that you should remove to carry out this fuel pressure test. To test a Volkswagen fuel pressure, disconnect the outlet fuel line at the filter and attach an inline pressure gauge. The engine must be idling, and the fuel pressure should be between 350 and 500 kilopascals. The next component that we're going to look at is the high-pressure fuel pump. Some interesting facts about the high-pressure fuel pumps used on each of the vehicles featured in this video are that they all use a single piston to create the high fuel pressure. They are all driven directly from the camshaft, and they all have a fuel pressure regulator on the pump. Most importantly, the pressure produced by this pump can only be checked using a compatible scan tool. Before working on the high-pressure system, always ensure you follow the manufacturer's procedure to remove the fuel pressure from the system. Some examples of safe methods are to use a scan tool to depressurize the system. If you don't have a scan tool, Wait at least 2 hours before opening the high-pressure system. And always ensure you're wearing the correct personal protective gear. Remember, fuel spray is extremely flammable. Always ensure that you work safely. Here is a schematic diagram of a high-pressure fuel pump. The shape and design of this pump will vary between vehicles. However, the main components listed here are universal. These descriptions can be found in your book on page 39. The fuel pump does not use an oil supply to lubricate the internal components, and petrol isn't adequate to lubricate the highly stressed surfaces, so the pump gets its lubrication from a Teflon coating. It's interesting to note that the number of cam lobes on the pump drive bears no relationship to how many cylinders the engine has. For example, Mazda's 4-cylinder DPI engine has 3 lobes on the camshaft. The high-pressure fuel pump operation can be split into 3 phases: the intake, the return, and the delivery phase. Let's have a look at each of these phases in detail. The first phase we'll look at is the intake phase. As the piston moves in a downward direction, it creates a low pressure, or suction, in the area above. Because the fuel pressure regulator solenoid is not energised, this valve is open and low-pressure fuel is allowed to flow from the fuel tank into the chamber above the piston. In the return phase, the piston starts to move upwards following the cam lobe. The solenoid is still off, meaning that a small amount of fuel is pushed back into the low-pressure line into the attenuator. The attenuator is designed to absorb and hold this returned fuel, ready for the next intake stroke. There are 2 parts to the delivery phase. In part 1, the piston continues moving upwards, and at a stage decided by the ECM, the fuel pressure regulator control solenoid is energised and the inlet valve closes. The pressure created by the piston is now directed out of the check valve and into the fuel rail. The ECM knows the exact position and the direction of travel of the pump piston thanks to the camshaft position sensor. It uses this information to energise the pressure control solenoid at exactly the right moment to deliver a precise quantity of fuel to maintain rail pressure. In part 2, at a pre-calculated point during the fuel delivery phase, the ECM de-energises the regulator control solenoid. The force of the fuel pressure acting on the back of the inlet valve means that it remains closed and the fuel continues to be delivered to the fuel rail. This method of operation allows the solenoid time to stabilise before it is re-energised again by the ECM in the next cycle. The Volkswagen engine has a 2-lobe camshaft drive, and as we saw earlier, the high-pressure fuel pump incorporates the low-pressure fuel sensor. This pump has the ability to operate at pressures up to 11,000 kilopascals depending on engine demand. Mazda use a 3-lobe camshaft to drive the fuel pump. When testing this fuel pump, Mazda specified the test to be carried out under 2 different conditions. The first test should be carried out at idle. The pressure specification for this test is approximately 3,000 kilopascals. The second test requires you to dial the pump load to 60% using a compatible scan tool and then read the pressure. The pressure specification for this test is 11,500 kilopascals. Remember, this pressure reading can only be tested using a scan tool. If you ever carry out work on one of these pumps, be very careful not to break the seal between this connection and the pump. If the union is allowed to turn during removal or installation, even by a small amount, Mazda state that the whole pump must be replaced. Holden also use a 3-lobe camshaft to drive the high-pressure fuel pump. Depending on the capacity of the engine that you're working on, there are 2 different specifications. The 3.6 litre engine uses a Bosch pump and will produce up to 12,000 kilopascals. The 3 litre engine uses a Siemens pump and runs at pressures up to 15,000 kilopascals. The next components to look at are the fuel rail and injectors. As the fuel injector tip must reach into the combustion chamber, you'll usually find that the fuel rail and injectors are located below the intake manifold. Gaining access for testing or replacement of either the injectors, the fuel rail, or the fuel pressure sensor can be difficult and usually requires the removal of the intake manifold. This is a Mazda that's had the intake manifold removed to give you a better view of how the fuel rail fits on the engine. This rail is made of cast aluminium and incorporates the pressure sensor and a pressure limiting valve. This is a Volkswagen FSI fuel rail setup. In this picture, we're looking at the fuel rail from beneath the cylinder head. The rail is slightly different in the fact that it's made from stainless steel, but still tucked away under the inlet manifold. Again, a pressure limiting valve allows fuel to escape back to the tank if the pressure exceeds 12,000 kilopascals. Holden's V6 engine uses 2 separate fuel rails with a bridging pipe to transfer fuel from one side to the other. The 3 and 3.6 litre engine fuel systems are designed very differently, and the fuel rails are not interchangeable. Both fuel rails are made from stainless steel and contain a fuel pressure sensor. On each of the vehicles we've looked at, the operation of the fuel rail pressure sensor is very similar. Each sensor has a 5-volt supply, a ground wire, and a signal wire. The ECM receives a varying signal voltage on the signal circuit depending on the pressure sensed. When the fuel pressure is high, the signal voltage is high. When the fuel pressure is low, the signal voltage is low. Mazda state that the fuel rail pressure sensor must not be removed from the fuel rail. If the sensor is diagnosed as faulty, the complete fuel rail assembly must be replaced. The high-pressure fuel pipes are different between the Holden models. There are 2 pipes for the 3.6 litre engine and 1 pipe for the 3 litre version. All manufacturers state that the high-pressure fuel pipes should only be used once. If the flange nut is loosened for any reason, the complete pipe must be replaced. As you can see, this pipe has been tensioned twice to show the effect that this has on the sealing surface. You can see the distortion that occurs, which creates a perfect seal when the pipe is compressed against the flange. The fuel injectors are solenoid operated and, depending on manufacturer, use up to 100 volts to fire. The tip of the injector fits directly into the combustion chamber, and in most cases, the injector is held in by the fuel rail bolts. Most manufacturers require the use of special service tools to remove the injectors for seal replacement or cleaning. At the time of filming, most manufacturers state that these injectors are not repairable, other than cleaning on a test bench. The fuel injector internal components are similar to that of a port fuel injector. However, the environmental conditions under which it operates are somewhat different. This is a scope pattern from a traditional EFI port fuel injector. It is negatively controlled, so when the circuit is earthed by the ECU, the injector opens. When the ECM opens the circuit, a voltage spike is induced in the injector circuit due to the magnetic field collapsing over the injector coil windings. Sometimes this spike can reach as high as 90 volts and can delay the closing time of the injector needle by up to 1 millisecond. A direct petrol injector signal is very different. The injector circuit is positively controlled, with the ECU supplying anywhere up to 100 volts. In this example, it initially supplies 65 volts to open the injector. It requires this high opening voltage to overcome the fuel pressure acting against the back of the needle. Once the injector has opened, the voltage is lowered to battery supply voltage and is held open with a duty cycle for the required length of time. To close the injector, it uses a negatively controlled signal. A duty cycle signal is used to control the amount of current flowing through the low resistance windings of the injector. Typical winding resistance is between 1.25 and 1.75 ohms. The fuel injectors for the Holden vehicles are different depending on engine size. The serviceable components are named on the screen and should be replaced whenever the fuel injector is removed. Notice that the seal on the injector tip is made of Teflon to overcome the heat of combustion while maintaining a good seal. One of the downsides to using such high fuel injection pressures is the injector noise that occurs due to excessive injector movement. The high voltage acting on the injector causes rapid needle movement, and this can be heard externally. To reduce this noise, an isolation cup is fitted to the fuel injector body, which is mounted between the fuel injector and the cylinder head. This is only fitted to the Holden 3.6 litre engine. The isolation cup absorbs some of the energy transmitted through the cylinder head and reduces the harsh ticking noise that can be heard on some other direct injection fuel systems. This is a wiring diagram for the Holden engine. You can see each injector is individually controlled by the ECM on both the positive side and the negative side of the circuit. The only safe way of testing the voltages in this circuit is to use an oscilloscope. Here is an example of some special tools that you'll need to remove and install the fuel injectors in the Holden engine. The kits for both engines are shown here. This is a Mazda fuel injector. You can see it is very similar to the injector we just saw, the only difference being that Mazda do not use Teflon to seal the tip. This is the only special tool needed for the Mazda. It consists of a removal tool with a slightly deeper cutout on one side to accommodate the electrical connector. Removing the injectors from the vehicle is relatively easy, providing you follow the instructions contained in Mazda's technical procedure for injector number 3. This instructs you to cut off a small section of the oil separator to allow access. This saves having to remove extra components. The operation of the Mazda injectors is similar to that of the Holden system, in that they use approximately 65 volts to open the injector, and then a duty cycle to keep them open. The differences are that they are not individually controlled on both the positive and the negative sides of the circuit, and that power is supplied to the injectors in groups of 2. To test these voltages, you should use an oscilloscope. A resistance test will return a result of between 1 and 1.2 ohms. The 2 oscilloscope patterns you can see on the right indicate how important it is to ensure you have the scale set correctly on the oscilloscope. These patterns have come from the same engine, but have been set to different scales. They show exactly the same information. This image shows the 2-litre FSI injector from the Volkswagen. Again, the items listed in the boxes around the injector are the serviceable components. The radial compensator does the same job as the isolator on the Holden and must be replaced every time the injector is removed. To remove this injector, you must break the tags off using a suitable tool. Operating voltages should only be checked using an oscilloscope, and the injector voltages are slightly higher than those previously seen. The Volkswagen injectors are opened using 90 volts. Then the voltage is reduced to approximately 30 volts to keep them open. The resistance of these injectors are between 0.5 and 2 ohms. Here is the service kit that is available for the Volkswagen injectors. And here is the special toolkit. It contains everything you need to remove and install the injectors. The next components that we'll take a look at are in the intake system, starting with the mass airflow sensor. The mass airflow sensor does exactly the same job on a DPI vehicle as it does on a port injection engine. It measures how much air is entering the engine and normally incorporates an intake air temperature sensor. Next is the electronic throttle body. The throttle body's design is not dissimilar to that of a port injection system. However, it can be used in a very different way. The left-hand side of this graph shows throttle angle. The line at the bottom shows torque produced from the engine, and the dotted line represents accelerator pedal position. In homogeneous charge mode, the throttle works in a similar manner to that of a port fuel injection vehicle. In homogeneous lean charge mode, the throttle plate is held at a greater angle than that just seen. This has a number of benefits. Any restriction normally caused by the partially closed throttle plate is reduced. The effect of exhaust scavenging is improved, which in turn improves volumetric efficiency. More air means a leaner air-fuel ratio. This does, however, cause some problems that need to be overcome, such as the loss of intake manifold vacuum, meaning that the brake booster requires a vacuum pump similar to that of diesel vehicles. The loss of intake manifold vacuum also affects when EGR can occur. This is where the manifold absolute pressure or MAP sensor comes into play. We'll look at this in more detail shortly. As we mentioned earlier, the high sulphur levels in Australian petrol means that manufacturers have deactivated stratified charge mode. If stratified charge mode were to be available to us, the throttle plate would remain fully open for most of the time and only closes slightly when EGR is required. Let's have a look at the manifold absolute pressure sensor. The design of the MAP sensor hasn't changed from the version that we currently use on traditional EFI-equipped engines. It may also be known as a boost sensor on vehicles with a turbocharger or supercharger. And it may also incorporate an intake air temp sensor. But most importantly, it has a new purpose, and that is to monitor manifold vacuum so the ECM can calculate when to operate the EGR system. The Holden 3.6 litre engine is the only engine we've looked at that doesn't use a MAP sensor. Next on the list is the variable intake manifold. First thing to note with the variable intake manifold is that this isn't a variable length intake manifold. This is a very different component. This kind of variable manifold controls how the air enters the cylinders of the engine. By opening and closing the intake manifold flap, the air can be sped up or slowed down, or it can be made to swirl or tumble. The variable intake on Mazda vehicles use an ECM-controlled vacuum actuator to move the intake manifold valves. Volkswagen use an electric motor with a position sensor to provide feedback. Holden do not use a variable intake on their engines. Here, you can see how the Mazda system is used. This system will only operate when the engine coolant temperature is below 60 degrees Celsius and engine speed is below 3,750 RPM. Looking at the picture, you can see how it alters the behaviour of the airflow into the cylinder. Volkswagen's variable intake changes depending on which injection mode is operating. Homogeneous lean mode is shown here. The intake manifold valve directs the airflow to one side of the intake valves, which causes a swirl inside the combustion chamber. The chart on the right shows the very limited window of operation of this mode. Earlier in the video, I spoke of how the different injection modes can alter the way the throttle plate opened and closed independent of the accelerator pedal movement. This change brings with it the risk of the brake booster running out of vacuum for efficient brake assistance. So manufacturers have had to find a way to overcome this. Methods include using a vacuum reservoir, commanding the ECM to close off the throttle plate when vacuum has dropped below a specified level, using a vacuum pump similar to that of a diesel vehicle, whether it be electronic or mechanical, or using an electronic booster. Holden use an electronic vacuum pump to create vacuum if the system senses that it is low. A vacuum sensor on the brake booster measures the vacuum level, and this is monitored by the ESP control module. Volkswagen used two different systems depending on which transmission is fitted. Models with an automatic transmission run a very similar system to that of the VE Commodore. The manual transmission version uses a sensor to monitor the vacuum at the brake booster. The ECM will command the throttle plate to close in order to increase vacuum when required. And Mazda do not use any additional vacuum supply pump on their vehicles at this moment in time. Now, let's look at the servicing requirements. The servicing requirements for a direct petrol-injected vehicle are very similar to those of a traditional port fuel-injected vehicle. From what we can see, the only change will be that a standard fuel injector testing and cleaning machine will not be suitable for a DPI injector due to the higher pressures and voltages required to operate them. Some common problems have been brought to our attention at Autotech. Here are a few of those problems. We've heard reports that Mazda DPI models have been suffering from leaking injector seals. Seen here in a closer view, the oily build-up around the injector indicates that the combustion gases have been escaping past the seal. On closer inspection, it was found that the sealing O-rings at the tip of these injectors were broken. The injector pictured on the left has had a heavy-duty aftermarket seal fitted. These are proving to be successful in fixing the issue. The injector on the right shows the standard factory seal fitted. These aftermarket kits should be available through your local Repco store. Audi have released a technical bulletin concerning their 2-litre FSI engine built between 2005 and 2007. The vehicle will present with DTCs relating to fuel pressure and fuel trim. The issue is related to excessive wear on the camshaft follower fitted to the high-pressure fuel pump. The recommended repair is to replace the cam follower with the modified version which has extra hardening. In severe cases, it may be necessary to replace the high-pressure fuel pump and the camshaft. This issue may also affect other vehicles within the Volkswagen Audi group using this engine. These pictures show an excessively worn camshaft follower as a result of this issue. Now let's look at E85 fuel technology. E85 fuel is also known as biofuel. It contains 85% denatured ethanol and 15% unleaded petrol. Denatured means that it has been mixed with roughly 4.5% of unleaded petrol. E85 contains only 70% of the energy of standard unleaded petrol. Users of E85 report an increase in fuel usage compared to unleaded fuel. Having a research octane number of 105 means that in a specially designed high-compression engine, E85 performs extremely well in high-power applications. Some manufacturers claim they have built dedicated E85 vehicles that achieve better fuel economy than petrol equivalents. E85 is not widely available even in metro areas, but it's on the increase. And just to note, ethanol-blended fuels should not be used for anything other than road transport use. Cars that run on E85 are often called flex fuel vehicles. The very first flex fuel vehicle was a 1908 Model T Ford and would run on anything from pure ethanol to pure petrol. Nowadays, a flex fuel vehicle is classed as an engine capable of running on anything from pure unleaded petrol right through to E85. A vehicle that requires two separate fuel tanks is not classed as a flex fuel vehicle. Therefore, dual fuel vehicles that use unleaded and LPG, for example, are not classed as flex fuel. And surprisingly, there are more than 22 million flex fuel vehicles on the road globally. The flex fuel Commodore and Captiva use a sensor called a flex fuel sensor. This sensor is located underneath the car on the side of the fuel tank. It measures the ethanol content in the fuel and fuel temperature, allowing the ECM to adjust ignition timing and fuel injection to optimize the engine running conditions. For more information on this sensor, please refer to your manual on page 77. Now let's revisit the questions asked at the start of the video. Homogeneous and stratified are words used to describe the different fuel operating modes in an engine. Homogeneous means that the air-fuel charge is well mixed. Stratified means that the lean air-fuel charge is layered by a curtain of air on the cylinder walls. A NOx storage catalyst is a device designed to capture and regenerate oxides of nitrogen, a byproduct of high combustion temperatures. These are not yet used in Australia. Vacuum pumps are often used on DPI engines due to the changed throttle plate operation and the possibility of insufficient vacuum to supply sufficient brake assistance. And the coil resistance for a typical DPI injector should roughly be between 0.5 of an ohm and 2 ohms. If you have any unanswered questions from anything you've seen in this video, please call our technical department on 1300 300 352, and they'll be more than happy to talk to you. Thank you for watching, and look out for the next Autotech training video.
Not so long ago, cars were pretty easy to fix and everything you needed was right there in your toolbox. These days, cars are more like computers on wheels, and having the right information is the most important tool of all. But where do you go to find this technical information? Do you spend hours on Google looking for answers? Or maybe you call a mate, assuming he knows what he's doing, spending countless hours that can't be billed and losing customers as you try to fix the problems time and time again. As cars become more complex and manufacturers publish more and more technical data, how are you going to keep up? Introducing Repco Autopedia, the ultimate resource for technical information that gives you more know-how for more cars. With extensive wiring diagrams, thousands of OEM-style diagnostic flowcharts, comprehensive component location images, and all backed up by our technical help team. Autopedia has over 1 million pages of technical information covering 52 vehicle manufacturers, all accessible via the easy-to-use website. Now let's see Autopedia in action. Using the example of a Volvo S40, 2008 model, fitted with the 2.4-litre engine. Let's get some information for the electric sunroof circuit by simply clicking on the wiring diagrams icon and selecting the sunroof diagram from the available list. Like all Autopedia content, these diagrams can be printed for use at the vehicle. Now let's see how Autopedia can help you sort out trouble code problems. Troubleshooting diagnostic trouble codes is as simple as clicking on the Diagnostic Trouble Codes icon and selecting the relevant code from the available list. These OEM diagnostic flowcharts are the same information that dealerships use to guide them step by step through diagnosing the problem. If there's no information available on Autopedia, the category will be greyed out. No problem. Simply click on the greyed out icon and a Tech Help request form is generated.
Just got your priority help email, and I want you to confirm it's the 2008 model. Okay, fine. I'll be sending that information to you in a few minutes.
Well, gone are the days of your points and plugs and things coming in for a quick tune-up. Now everything is very electronic based. Almost have to be a computer technician rather than just a mechanic. A car that's got an electrical problem, we need to be able to first diagnose it with our tools, etc. Then we need the information on hand. That way we can actually work through a process to find out what the problem is and resolve it. The biggest thing we find is we can actually get the job done a lot faster, okay, because the information's here. I'm not faxing for information, I'm not ringing people trying to get a bit of a favour, can you send me some information on this? It's all held within the program. It means our diagnosis time is much faster, everything's on hand, we get the job done and car back straight away to the customer. Saves a heap of time, in turn a heap of money. Thoroughly recommended. The process just works from start to finish. Fantastic.
With Repco Autopedia, you have access to the OEM quality data you need to diagnose and complete repairs quickly, meaning you fix it right the first time. For immediate access to your 30-day trial, go to autopedia.net.au and hit the Register Now button. Repco Autopedia. More know-how for more cars.